that whether a particular data is coming from a particular distribution. Okay, so that is called the chi-square test for goodness of fit. And I have considered two cases. In one case where we don't know the form, I mean the distribution is completely specified, and the second one is that the distribution is partially specified. So then there may be unknown parameters in the distribution. The test is chi-square in both the cases. However, when some parameters are not known, then we have to estimate them from the data, and the number of degrees of freedom gets reduced equal to the number of parameters that you are having. Now this chi-square test for goodness of fit is actually useful for some other tests also, some other type of testing problem. So let me tell that thing. So many times we have data on the attributes. Okay. So attribute can be, for example, you can have income levels and then the level of education. For example, can you say that the people who are having higher level income group, I mean higher level of education, they will belong to the higher income group and vice versa, and the people who are in the lower income group, they will be having lower levels of education and vice versa. Okay. So suppose we want to study this thing and some data is collected. So we want to find out whether the two things are related. That means the levels of educational levels and the income levels. So the general problem of this, it is called the testing for independence. Testing for independence in R by C contingency tables. So the contingency table, it will be represented like this, that you have say A and B, and A has say R levels and say B has say C levels. So the data, we have a random sample of say size n from the population, and Oij is the frequency of the cell corresponding to ith level of attribute A and say jth level of attribute B. Okay, so how we can write the data in the form of a table? We can put it like this. So we have levels A1, A2, AR, and on this side say B1, B2, B, C. Okay. So this observed frequency will be O11. That means, say for example, I mentioned A as the income level and B as the educational level. So in that case, you may say that the person with the highest educational level and income level, that is O11 is the frequency. So similarly, you will have O12 and so on, O1C, O21, O22, O2C, and so on, OR1, OR2, ORC. We can also look at the totals column wise and row wise. So first column total I will write here C1, C2, CC, okay, and the row totals we can call it R1, R2, RR, okay. So these are the row totals and column totals respectively. We want to test whether the attributes A and B are independent or not. For that purpose, we will calculate again the expected frequencies in the following fashion. This total is N. That is equal to Ri into Cj divided by N. And the formula then is double summation Oij minus Eij square divided by Eij. I is equal to 1 to R, J is equal to 1 to C. W has approximately chi-square distribution on R minus 1, C minus 1 degrees of freedom. So the hypothesis H naught is attributes A and B are independent against the hypothesis that they are dependent. Then the test is we reject H naught if W is greater than chi square alpha R minus 1 C minus 1. Okay, let me give one example here. This is the data on A is the income level. So A1 we can say to be high income group. A2 is say upper middle. and then we have, say, lower middle, and A4 is, say, low income group. Similarly, suppose I have 3 education levels, and I consider, say, B1 as the more than average, B2 as, say, average, and B3 is, say, below average. And a random sample of thousand is taken, and so I'll make it in the form of a table here. So this is 78, this is 112, 110, and 30. So that this total is actually, the column total is 330. This is 80, this is 110, this is 100, this is 50, this is 340, this is 85, 105, 95, 45. So this is 330. We can write the totals on this side also. So we have the row totals and the column totals. So from here, you will calculate the expected frequencies. For example, these are the observed frequencies. This is O11, this is O12, O13, O21, O22, O23, O31, O32, O33, and O41, O42, O43. Now you will calculate E11. What is E11? That will be 243 into 330 divided by 1000. Similarly, E12, that will be equal to 243. So that means basically, if I am looking at a particular cell, the expected frequency of that cell, you can just look at the corresponding totals on the row side and the column side and multiply and divide by the total n here. So this is 243 into 340 divided by 1000 and so on. Okay, so you can do this calculation and then calculate the value of W. Now W can have another simplified version also. We can expand that, and that formula becomes I is equal to 1 to R, J is equal to 1 to C. So this is the simplified version also. Whatever is convenient, I mean, this is basically a computational problem. So one can calculate this thing. Okay, so is this problem and the test procedure clear?
Yes, sir.
There is another one. The similar, I mean, the test function will be same, but it has another application also. Okay. So this is contingency with one margin fixed. And this is called test for homogeneity. Okay. Earlier, we have taken a sample from the total population and we categorized into cells. But sometimes we have to take either row wise or column wise samples. So I am presenting the problem in that way. Suppose independent random samples of sizes R1, R2, RR are taken from R populations A1, A2, AR respectively. So this is data is taken row wise here. Classifying the each sample here row totals are fixed here. So we want to test whether the categories are homogeneous. The test function actually remains the same. Okay. So this chi-square test for goodness of fit, it is actually an essential component of the tools for testing of hypothesis. So initially I have mentioned to you the Neyman-Pearson theory, and the Neyman-Pearson theory allowed people to solve large number of problems of different kind and to get the most powerful test, the uniformly most powerful test and the uniformly most powerful unbiased test of various hypotheses. Okay. This chi-square test does not fall into that category. That is why I have done it in a different, I mean, separately, because this you cannot derive in the most powerful fashion. I mean, it is actually a test which is basically an asymptotic test, or you can say an approximate test. So I am not saying it is a uniformly most powerful test or any such thing. However, it is one of the very prominent tests for modeling of the distributions. Like so nowadays also and earlier also, I mean, the data sets are available in the field problems. When the field experiments are there, you usually get a large amount of data. Now, in order to apply any, for example, any particular estimation procedure or any testing procedure, we have to have an assumption that it is from normal distribution or it is from exponential distribution, etc. So it should be justified. So first thing is that we do is that you plot the histograms, make the frequency curves, and then apply the test for goodness of it. Additionally, this test has been found to be useful for testing for independence of attributes, for homogeneity of categories when we have categorical data. So various kind of things can be done through the same test. Okay. Is this discussion clear to all of you? Is it okay? I'm not able to hear. Is there some problem? Are you able to hear me?
Yes, sir. It's clear, sir.
Okay. In the testing of hypothesis, I will not cover anything more right now. I mean, I think we have covered a substantial amount of testing procedures. So I will not cover anything more in this thing. In your probability course, I hope all of you had some exposure to the confidence intervals. Did you cover confidence interval for some say parameters of the normal distribution? In your testing in the probability and statistics course, the first course?
No, sir.
It was not covered. So very quickly, I will just introduce the topic, and we will do it for say parameters of the normal distribution. Okay. So suppose I have a sample, let x1, x2, xn be a random sample. From a population with some distribution, say fx theta. Okay. Let us consider say two statistics tx, t1x and t2x are two statistics. Okay. If probability of t1x less than or equal to g theta is less than or equal to t2x is equal to 1 minus alpha, then t1x to t2x is called (100) 1 minus alpha % confidence interval for g theta. What is the meaning of this? It means that if I am taking, suppose I say alpha is equal to 0.05. So if I say I have taken 100 samples, then out of 100 samples, the interval t1x to t2x will contain the true parameter value at least 95% of the time. So this is the meaning of the confidence interval. So higher the confidence coefficient or the confidence, this one minus alpha, it means that we are more sure of our estimation procedure. In point estimation, we actually give one value for the estimate. Like we say, what is the average income? So you say 9,000 rupees. But it is better to speak something like this, that the average income is 8,500 rupees to 9,500 rupees, with at least say 95% confidence. Okay. Then this is a more, you can say, informative and more accurate statement compared to saying that the average income is 9,000. Because if you say 9,000, then I may have another sample where the value may turn out to be 9,000, say 10 rupees. Okay, so then it is changing. But rather than that, if we give an interval with a certain confidence, that is a much better way of statistical inference. Okay. Now there are methods. So what should be the good thing? The good thing should be that 1 minus alpha should be very large. Like I mentioned, 95%, you can have 99% and so on. And the length of the interval should be small. Like if I give one statement that 95% of the time the average income is between 8,500 rupees to 9,500 rupees. And another statement is that 95% of the time average income is 8,900 rupees to 9,100 rupees. Then my second statement is better statement because it has a smaller interval with the same confidence level. Okay. So problem of finding out shortest length confidence interval became a major statistical research issue. And it turned out that if we can find out the most powerful test, the uniformly most powerful test, etc., then the same procedure actually gives you the best confidence intervals also. And in fact, this entire theory was again developed by Neyman Pearson themselves. So now we don't have that much scope of actually going into the theorems and proofs. Rather, I should tell you the practical procedures that we have developed. I mean, they have been developed by statisticians for different problems. So in general, let me start with the normal distribution. Okay. So confidence intervals for parameters of normal populations. So x1, x2, xn is a random sample from normal mu sigma square. Okay. So confidence interval for mu. First case is that sigma square is known. If sigma square is known, then the confidence interval is x bar minus sigma by root n z alpha by 2 to x bar plus sigma by root n z alpha by 2. Okay, this is 101 minus alpha % confidence interval for mu. If sigma square is unknown, then we replace this sigma by s, and this z will replaced by t on n minus 1 degrees of freedom. So this is 101 minus alpha % confidence interval for mu. Okay, so are these two statements clear to you?
Yes, sir. Yes, sir.
Okay. Similarly, confidence interval for sigma square we can write if mu is known, then it is sigma xi minus mu square by chi square alpha by 2 n to sigma xi minus mu square divided by chi square 1 minus alpha by 2 n. So this is 101 minus alpha % confidence interval for sigma square. And if mu is unknown, then this is replaced by n minus 1 s square by chi square alpha by 2 on n minus 1 degrees of freedom. On n minus 1 degrees of freedom. Okay, so this gets changed here. Maybe I think I should stop this course at this point of time. Actually, I have covered quite substantial material. I mentioned to you that I will be giving one problem set for testing of hypothesis and confidence interval. So maybe by today evening I will send to you. You just solve those problems and do some practice for that. And I will inform you date of exam and so on. Maybe in the next class we can discuss that date of exam, etc. Because I don't know what is the final thing, online, offline. A lot of confusion is there. So I think it has been told to give the option, and I have not yet got any notice from the exam academic section regarding exact method of conducting the exam. But whatever be that, you please prepare the problems, and the syllabus will be whatever I have covered after the mid-semester examination. Because after mid-semester examination, substantial portion has been covered, so we'll look at that thing. If you have any questions, otherwise I will stop the class right now. Okay. Do you have any more questions or anything to ask?
No, sir.
Okay. Okay, then I will be stopping. I will inform about the exam and the time in the next class. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay, all the best. You please
Thank you, sir.
prepare well for the exam. Okay.
Yes, sir.